Last part of midterm, problem 3, part D. We want to prove that encryption and decryption function are inverses. So we want to prove that d of e of x for any message x is equal to x, or equivalently we want to prove that x to power ed is equal to x mod n. And n here is product of three primes. I call them p, q, and r. Also we know that d is equal to e inverse mod p minus 1, q minus 1, r minus 1. So let's simplify x to power ed minus x by factorizing an x. So it is x to power ed minus 1 minus 1. We want to prove that this is 0 mod n, and since d is e inverse mod p minus 1, q minus 1, r minus 1, we can write ed minus 1 as k some integer times p minus 1, q minus 1, r minus 1. So I want to show that x times x to power k p minus 1, q minus 1, r minus 1 minus 1 is equal to 0 mod n. Okay, so I will erase the top two lines. In order to show this, I will show that all the three primes p, q, and r divide this number here. So I can show that p divides this number. Similarly, it can be proved for q and r. To show that p divides this number, I consider two cases. The first case is that GCD of x and p is 1. So when GCD of x and p is 1, I can use the Fermat's Little theorem, which states that x to power p minus 1 is equal to 1 mod p. So x to power p minus 1, the whole to power k, q minus 1, r minus 1 minus 1 is equal to 0 mod p. So this shows that in this case p divides this number I call a. Let me erase this line to go to the second case. So second case is that GCD of x and p is p itself. This case is trivial since a has a factor of x, then immediately we have that p divides a. So similarly, let me erase this line. Similarly, we can prove that q divides a and r divides a. Now since p and q and r, all of them are prime numbers, we can deduce that p times q times r divide a, because a needs to have all the three factors p, q, and r. So this proves that n divides a, and this is what we wanted to show. So a mod n is equal to 0, and the proof is complete.